Can you hear well? Can you hear well? Do we need to turn on the speaker? Yes, the speaker. We have right. Yes. Okay, thank you.
Okay, can you hear me?
Yeah, yeah, we are ready. We
All
are
right.
ready.
Okay, so like I say, I won't be using the halfway break. Can I finish the class early, like 15 minutes before 6? So around 5:45 p.m. Malaysia time. Is it okay? All right.
Yes.
Okay. So can you see my screen? Oops, where is it? Can you see my screen?
Yes, we can see the stuff.
All right. Okay. Perfect. Okay, thank you, Mr. Hugh, again for the invitation, for the third lecture for TR rocket engine for 05 engines. So today we will discuss a little bit about the flight performance of a rocket lah. Okay. So as you know that last week you have a lecture with Dr. Hugh on the nozzle designs or nozzle performance, which is more heavily mathematical formulas and everything, all your knowledge on thermodynamics, heat transfer, everything is put into that particular chapter. I have seen the notes that you shared in the Google Drive. So yeah, for me, I think it is many. Okay, it is many. It is like full of what do you call it? Formulas, equations, and etc. I hope the students manage to understand. But let's say if you want to have a consultation with me, you can also contact me. Dr. Hugh can send them my email. But for your life to make easier, let me share you something that you can use rather than do all the mathematical formulation. Of course, you need to know those mathematical formulation, but you can start Google what we in the website. There is some like a calculator on how to determine this. Okay, you can go to the Richard Naka's naka-rocketry.net. This is free available, so you can see from his work. He actually provides some of the calculation tools that he made to develop or to build sounding rockets lah, like this hands rocketry software and etc. You can take it and use it. Okay. For example, open motor rocket, uh, burn rate cycle, hollow cell, and etc. You can browse through this website for you to use it for free. And again, brothers and sisters, usually when I taught the last chapter, yes.
Yes. So can you type the name of the website on the chat box?
Oh, okay. All right. Let me type the name of the website. Okay, so this is, let me copy and then send this to the chat. Okay, there you go. Okay, so
Thanks.
so this is some calculator that you can use to calculate a few parameters, performance parameters. Other than that, brothers and sisters, usually what my students did is they take all the, let me see again, your formulas. Okay, what is your formulas? This one. Okay, nosatory. Okay, so what they do is they take all the formulas and this in a spreadsheet, in the Excel sheet, Excel file. You have input parameters, you have output parameters. So I can also share this file with you, what my undergraduate students have done. But of course, this is students' work, and it is their own initiative to build their own calculator. Because if you look at the calculation, all this calculation is troublesome. You have many, you have, yeah, oh, how many are more than 30 equations that you have to, you have to do. But again, this is all the basic, and usually when we practice, when we build our rockets, we do have this. But of course, you need to know what are the definition of each term. For example, this one, specific heat, internal energy, enthalpy, all those things, a definition you have in your thermodynamics. These are all thermodynamics. The first part is thermodynamics parts, and then the later part, of course, you have heat transfer. And brothers and sisters, please try to understand about the isentropic relation. This is very important. Isentropic relation. We assume that in the nozzle we use isentropic relation. What do you understand isentropic relation? It is adiabatic, and of course, there's no adiabatic, no heat transfer, and it is the change of enthalpy is, the change of entropy is zero, and it is an ideal condition. And this equation, this relationship shows the relation between pressure and temperature, density and temperature, specific volume and pressure, and the other sort of things. So another thing that you have to know, that this gamma, yeah, this gamma, some we call this gamma. Some books, it is K lah. Okay, so in your book, in your notes that you refer to, is gamma. Gamma is CP over CV. It is the specific ratio. This is needed. The gamma is needed where in the isentropic relation. This I'm not sure whether you feel grateful on this relation or not, because to have this relation, actually you have they have gone through many, what they call it, TDS relation, Gibbs equation, and etc., to get this sign, this relation lah. To appreciate this, to derive this, actually it is a tedious amount of work actually. All right. So yep, again, this is all the thermodynamics property. You have not yet go through the, what do you call it, this one is still thermodynamics. um, and of course, you when it comes to the later part of the notes, you have thrust equation, and please make sure that you manage to define the station. Okay, in order for you to calculate the nozzle performance, you need to know the station. For example, station 1, like this one is station P1. P1, the subscript 1, it is at the chamber, and then you have throat, and then you have the exit condition lah. Okay, what is R, you must and then gamma, yeah, this is the TDS relation, and as well as the, what do you call it, characteristic velocity. You have P exit, Mach throat, and etc. Those are the some of the definition that you must know in that particular chapter. Actually, the chapter on nozzle theory is a huge chapter. Actually, it when I teach this chapter, I have to take at least 2 weeks to cover this, because including the definition and etc. But anyhow, Dr. Hugh is very good, so she managed to do this in 1 week. So congratulations to her lah. All right. So yep, you can use that one, Naka, and I will also share you. I try to find back the Excel sheet, the spreadsheet that you can use to calculate all those parameters, because this is very tedious, especially if you want to find the design condition of the CF, coefficient of thrust, and etc. The equation is very long. See, like this one, CF, the equation is very long, and to do this manually is kind of hectic. So usually what I did, during quiz is an open book quiz, during exam is an open book exam, during final exam also an open book exam. So it depends how Dr. Hugh wants to do this with the class for the assessment. All right. Yeah, see, the equation is very long. And I hope that you understand each term, because equation is equation lah. But how you want to replace, how you want to substitute the value into the equation, that you must know. For example, this one lah, you can see that you have CF. CF is equal to thrust over P, product of P naught A star. So you must know what is P naught. It is a stagnation pressure. What is A star? It is the area at the throat where Mach number is equal to 1. Okay, anything star, that is Mach number is equal to 1. So all those things, CP, T naught, this is the relation of CF, which is coefficient of thrust. By the way, coefficient of thrust, you don't have unit, but it shows the magnitude of this design rocket in terms of the pressure ratio. Okay, this is why is it important. It is dimensionless, all right, dimensionless. All right. So anyhow, I hope you managed to cover the nozzle theory, the lecture of nozzle theory. You have four notes there, okay, 4 files there for you to cover. So now, okay, let's come back to my chapter. My chapter is related to flight performance. Okay, flight performance. Let's us recall from our previous lecture, my lecture in the first lecture, you know that um, in a flight, okay, in a flight, you have launch, orbit, and re-entry. Okay, so now we are talking about the flight performance, which is from launching, orbiting, and re-entry. And just to recap back about this slide. Okay, so when you go up into the mountain, you throw something, for example, stone, 3 kilometers per second, you will drop. And then if you throw much faster, it will drop 5 kilometers per second, drop further lah. Okay, 6.5 kilometers further until you achieve what we call as an escaping velocity. So it won't fall down back, and it starts orbiting. So this is what we call as the escaping velocity. All right. So now we want to know how these things happen. So this chapter is today. All right. Flight performance. Okay, so why you all know from the first lecture that rockets are needed because to do a mission, okay, many missions. So the mission for which rocket system is used is driven by many factors. Okay, maybe it is a military missions, maybe it is a commercial missions, or maybe it is a science mission. So for example, a military mission, it might need to deliver a payload to a target or place of a craft, such as spy satellite, or maybe a particular orbit in space, or maybe to send a missile or missile, for example, ICBM lah, intercontinental ballistic missile. So this is example for military missions. For commercial missions, it can include something related to the telecommunications, or maybe delivering satellite television broadcasts globally, or even a space tourism. So space tourism that we have, of course, like a Blue Origin, SpaceX, as well as the, what do you call it, Virgin Galactic lah. Okay, science mission. Okay, missions to put something, for example, telescope, for example, probe, or maybe a deep space mission to determine, for example, to determine the what do you call it, nowadays, perseverance, our Mars rover, not now, I think last night NASA has claimed that they have found the nearest evidence. Perseverance, it is a robot in Mars. They have found a proof of life in Mars, the closest one, because kind of minerals in not in a lake, in a, yeah, 3.5 billion years ago lake. It was a lake in 3.5 billion years ago, but everything is drying, but small patches. It is like some kind of minerals that can exist life. So you can Google this. It is a big news, great news for the scientists. But the problem is, although they can view this in what do you call it, telecommunication at far, but anyhow they need to bring the sample back at home. So as you know that now, American NASA, they don't have plan to take the sample back home, so they are opening for other companies to do this. So I think one of the company, Rocket Lab, they try, they want to do this mission, to take back the samples. So yeah, from that we can actually understand there is probably life exists in Mars. So this is the closest that the human being found in Mars. So that's a science mission lah. Okay, so that's a science mission. So looking at the slides, so we will do something related to, of course, gravity free, drag free spaceflight. So we will assume several things, huh? For example, you don't have drag, you don't have we don't consider the spherical influence of the earth. We consider it's a flat earth. And then it is drag free, gravity is constant. So yeah, gravity constant. But as we know that gravity depends on the r, which is the distance between one body to the other body. As you go up, actually the gravity pull, the force is reducing lah. Okay, reduces. So this is what the thing that we need to put assumption on, so that we can use the equation of motion to determine the ballistic or the parabolic curve of this rocket. Next, forces acting on the vehicle in the atmosphere. So of course, in your aircraft, you have lift, you have drag, you have weight, and then you have thrust. So we will be using that equation again. But maybe you can ask, we don't have wing. Yeah, I know that we don't have wing, and rarely you can see that. You can see that later, the lift generated by the body, the rocket itself, or maybe the fin is not that big. Okay, for example, the CL lah, the coefficient of lift as compared to the wing on an aircraft. Basic relation motion. So you can see that we're going to have use the relation of F equal to ma, the Newton's second law. But of course, you have two direction lah. One direction in on x and another direction in directional. Space flight maneuvers. And why is space flight maneuver? Space flight maneuver is you want to adjust something when you have perturbations in space. Effect of propulsion system on flight performance. Oh, this is important. What are the factors that contribute to your flight performance or the vehicle performance? So what things that you must consider? I usually ask this in the exam. Maybe I can ask this during the class, the quiz as well. What are the factors needed to improve the performance of your vehicle, your rockets lah? Okay, and then last one, of course, the flight vehicles. So you can stop me if you don't understand, or maybe I talk too fast, but bear with me. All right. So this chapter is to introduce the flight performance of rocket propelled vehicle, such as spacecraft, space launch vehicle, missiles, or projectiles. Again, a rocket is an engine. Okay, so this engine can push spacecraft. This engine can give thrust to the space launch vehicle if it used to launch something to space. And also this engine, rockets, for missile, to send what they call it, weapon warhead to what do you call it, to destroy something lah. All right. So propulsion system deliver a force. Propulsion system, which is the thrust chamber. When I say thrust chamber, it includes the nozzle and also the chamber itself lah. Okay. Force. The propulsion system deliver force to a flight vehicle and cause it to accelerate or at time decelerate. Okay. Looking back, recall back to chapter number 1. You can see that launch vehicle, for example, yeah, rocket, SpaceX, and etc., the acceleration at the beginning is quite slow. The thrust to weight ratio is not that big when you are having a launch vehicle. As compared to missile, the thrust to weight ratio, which is the contribute to the acceleration, is much faster. All right, all right. And then you need this propulsion system to overcome drag force. So, of course, in the atmosphere, you know that at lower altitude, you have air. Okay, you have air, so you have a lot of pressure. You have lots of what do you call it? Gases. So this gas contribute to contribute to drag. Let me switch on the aircon back. All right, sorry. Overcome the drag force, and again, it is used to change the flight direction. So maybe you want to maneuver, you want to go to the mission, interplanetary mission, you want to change the, what do you call it, orientation, and etc. So flight mission, in this certain book, he said that it can be classified into several flight regime lah. Maybe you have flight within the Earth atmosphere. For example, air to surface missiles. Okay, you have air to surface, or surface to surface, like internal ballistic missiles. You also have short range missile, surface to air missiles, air to air missiles, assisted takeoff units, sounding rocket. What is a sounding rocket? Sounding rocket is a rocket that you, like a technology demonstration, you shoot upwards, maybe 1 kilometer or 10 kilometer to the air, and then it goes downward. That is a sounding rocket. It's a projectile. It doesn't carry any weapon. It doesn't carry any. It can carry payloads, for example, altimeter, avionics system, and etc. Aircraft rocket propulsion system. Number two, it also can be classified as a near space environment. For example, a satellite, orbital space station, or long-range ballistic missile, such as ICBM lah, intercontinental ballistic missile. So we are talking, when mentioned intercontinental ballistic missile, so you are talking about more than 5,000 kilometer range and above. Lunar and planetary flight. Okay, so lunar mission to the moon mission, like Artemis mission, and then planetary flight. So, for example, Earth to Mars. Okay, deep space exploration and sun escape. Deep space exploration to go, maybe to go to the Pluto, like Voyager 1 and Voyager 2. Sun escape, for example, Parker. Okay, Parker probe that they have sent. All right. So now this is some of the thing that we need to simplify it. Okay, before I discuss with you on the gravity-free, drag-free space flight. So you also must know that you have a rocket. Rocket is a engine, and then you have a payload. Payload usually they put this at the nose or maybe at the body. So if you are talking about a payload, it can be, or if military, it can be a warhead, it can be science instrument or communication device lah. Okay, so whatever the missions and whatever the payload, there is always the need for understanding the rocket science and engineering principles. For example, the chapter 2 lah, which govern how to put payload and where it needs to be, and how to control it once it's arrived at its mission destination. So, brothers and sisters, it is like this. When you the philosophy of this rockets engine course, usually number one is to determine the mission. This is the first thing that you must know. Okay, for example, the mission is to put 10 kilometer of payload. Okay, so you must know the mission first. From the mission, from the Tofsky equation, like what we are going to learn in this chapter, you will know how much the mass, the propellant mass that you can put, how much payload mass that you can put. So from the mission for this chapter, then you go back to the nozzle design in chapter number 2. Okay, it is something like that. Okay, all right. So uh, coming back to the trajectory. Okay, so you have trajectory on the ballistic, which is the trajectory, the what they call it, the moving object. Okay, the trajectory lah. Okay, you know that it does not ascending vertically upward straight. Okay, you have the rocket goes straight and then incline. So from this characteristic, where the orbit is planned for the mission, the rocket scientists and engineers usually determine the appropriate launch vehicle. So you know that, okay, you know this is the mission, and when you calculate, you need a certain delta V, delta U in this chapter, okay, delta U. So the delta U it can determine the appropriate launch vehicle, what to use, what kind of upper stage rockets that you want to use, for example, multi-stage rockets, and onboard thrusters to complete the mission successfully. Okay, all right. So, of course, you have to start with the simple trajectory first for this chapter and how to calculate them. Lah. Okay. Because once the rocket is launched, okay, when rocket is launched, it burns the fuel until it completely shut off. Okay, this is what we call as this is what we call as MECO. Okay, main engine cut off point. MECO. So in the public, it's like a sounding rocket, like hobby rocket lah. Okay, so you have a solid fuel. So when you launch a rocket, okay, when you launch a rocket, the rocket is ignite and burn, and few second it will burn. It will burn out. Okay, and then due to the what they call it, inertia, with its momentum, so it can still fly with its inertia and momentum. Okay, so MECO, it is when the main engine cut off point. So it can travel when we assume it is drag free, gravity free, and etc. It will start to fly parabolically. Okay, parabolically. So similar like in launch vehicle. Okay, so you have main cut off point, and then if you want to turn on the second engine, there is an argument. Okay, for example, in SpaceX, you can see the Starship. The first in the early experiment of the Starship, there is an argument when the second stage engine after the main engine cut off, or when the main engine cut off is about to finish, this upper stage, the second stage, is turned on. Okay, so there is some debate there. So eventually they come up with a new design, which is successfully. They switch on the second engine, the upper stage, the second stage, on before the main cut off engine. Okay, before they cut off the main engine lah, MECO. All right, so to be safe, but in order to do so, they have to design the structure to withstand, because it is stacking. You have a Starship and then you have a booster. This booster must equip with a thermal resistant structure that can withstand hot gas coming from the second stage. Okay, so that is different case lah. All right, so once the rocket is launched, it burns its fuel until it is gone. This is what we call as the engine shut off. At that point, the vehicle has reached to the so-called burnout velocity. So when MECO happen, main engine cut off happen, this is what we call as burnout velocity. At that point on the rocket path, it becomes freely flying projectile, unpowered and forced to succumb the laws of physics of a projectile motion. But in order to do this, gravity-free, drag-free space flight, okay, we need to have several assumptions. And this assumption is legit, is valid, because they have used this for many cases. Number one, what are the assumptions? Acceleration due to gravity is assumed to be constant. This is the first assumption lah. Okay, the first assumption that the gravity is constant. And it is actually, you know that the gravity pull depends on the distance between m1 and m2. If you look at the equation, gravitational force equation, Fg is equal to G m1 multiplied by m2 divided by r square. Okay, so yes, m1 is the mass of the earth, m2 is the body, the flying body, which is the rocket itself. M2, and to compare M1 and M2 is uncomparable, because the mass of the Earth is much bigger, much larger than M2, the rocket itself. So actually, you can neglect that. But in reality, in physics, the gravity is not constant. It's not constant, depends on the Earth, depends on the height, or the R, which is the distance. It also depends on the mass. If you look at the, what do you call it, the shape of the earth, it is round and it is bulged at the equator. So actually the gravitational force at the equator is much larger compared to higher latitude, for example Norway or Finland, countries at the higher latitude. Why? Because m, okay, at the center of the earth the mass is much bigger, because it is bulged at the center, at the equator. So that's why the gravitational pull at the center is the gravitational force pull at the center is much larger. Is much larger than the higher altitude. That's number one assumption. Number two, they neglect the air resistance. Although during launching you have atmosphere. Number three, we assume that the Earth is flat. Okay, that is to make it life easy lah. Number four, we assume that the Earth's rotation has no impact on the motion of the projectile. So you know that the Earth is rotating. We assume to do this, to use the equation, we assume that the Earth rotation has no impact on the motion of projectile. So those are the four assumptions that we make to simplify the flight analysis to outer space environment. It must be far enough from any star, because when you have star, you have planets nearby, it actually pulls you. They have a gravitational pull, because the force, you know that the gravitational force depends on the matter, on the mass of a matter. So when you have two body, for example, the Earth and the Moon, so you actually, it's a three body problem lah. Okay, where there's no atmosphere, there's no drag, and essentially no significant gravitational. Okay, so but we also assume this one, the flight direction is the same as the thrust direction. So the thrust, okay, thrust is a force. So force is a vector where you have magnitude and direction. So we assume that the thrust direction is the same as the flight directions. Where is it? It is along the axis of nozzle. So you have a nozzle. Do I have a nozzle here? Let me check. I have a nozzle here. So let me this nozzle. Oh, I hope you can see my nozzle. Where? Okay, let me stop presenting. So this is my nozzle. Okay, this is my nozzle. Okay, you can see that if the axis is direction to the thrust is direction to the axis of the nozzle, means you're talking about here straight. So this is nozzle. Okay, the nozzle. So it is here. Okay, so this is the direction of the thrust. All right. direction of the thrust. Okay, in the middle. All right. So that's that's how that is the assumption. Okay, let me share back the screen. Quite difficult to teach online class. So let's come back to the slide. Okay, so along the access nozzle, so this is what we call as the linear acceleration path. Okay, so the propellant mass flow, which is the m dot. Okay, m dot is very critical. I hope you understand this. M dot is a mass flow rate. It appears in the equation, the thrust equation. T is equal to m dot VE, which is the momentum thrust plus the imbalance pressure. So m dot, like I say in the first class, to achieve a high thrust, you can either expel the air, the propellant at big enough, which is m dot, or at high speed, which is the exit velocity. And the propulsive thrust F remain constant for the propellant burning duration TP. Okay, so during the using this flight performance equation, we also assume that the thrust is constant, remain constant. In reality, no, it doesn't happen that way. Thrust actually changes with altitude, with time, and etc. It depends on the type of fuel. If we are talking about solid fuel, okay. So in a solid fuel, the geometry of the fuel determine whether the thrust can be constant, which is constant burning, or it is progressive burning, or it is regressive burning lah. Okay, so it depends on the geometry. If you are using what do you call it, liquid fuel, okay, so you can throttle, and again the changes in altitude, it will the P ambient, okay, pressure ambient. So when pressure ambient changes, you cannot have a design condition. Design condition, it is where exit pressure equal to ambient pressure. When we want to design the nozzle in the previous chapter, we must assume that exit pressure equal to ambient pressure. Exit pressure means pressure at the nozzle exit must equal to ambient pressure. This is how we design a nozzle. We call this an ideal nozzle. For any rockets where the start and blow down duration can be neglected, okay, so during the firing, ignition, and also during the shutdown, it's kind of very shorter times. So this is what we assume it is neglected. The instantaneous mass of the vehicle may be expressed in the function of time using the initial mass of full vehicle m naught. Okay, now you have to remember the definition. Okay, full vehicle m naught, which is the total amount of mass for everything before it launch. M naught is initial mass. Okay, initial mass of the total vehicle, including payload, including the structure, including okay. The initial propellant mass is MP. So M naught is initial mass. MP is the propellant mass, which is the fuel and oxidizer you want to bring. And also you have TP, which is the cut off power. This is where your MECO is about the time, okay? The time for the MECO. So it follows M. M is instantaneous time. Instantaneous time, it is, for example, you want to calculate the mass of a vehicle, the launch vehicle, at 4 seconds. Okay, so M here is an instantaneous mass. Okay, is equal to m dot, which is the initial mass before launch, minus mp over tp and t. Okay, mp is a propellant mass, tp is a cut off mass. Okay, cut off mass, cut off time. Okay, power cut off time. And t is which second are you referring to. So you can arrange take m naught outside. So you have m naught is equal m is equal to m naught in bracket 1 minus mp over m naught t over tp. So you can see that you have mp over m naught, mass of the propellant divide by m initial. So this term we call it as zeta. This is the denotation, zeta. Okay, zeta here. Zeta is mp over m naught, mass of the propellant over initial mass. So actually, zeta plays a very crucial role. If zeta is higher, means that you carry more fuel. We are expecting we expect that if the vehicle carries, for example, zeta 0.8, so 0.8 means that 80% of the total mass of the vehicle is fuel, propellant. Okay, propellant. Okay, so the higher the zeta is better lah. Okay, so zeta is mp over m naught. Okay, multiplied by t over tp. Or zeta by definition is 1 minus mr, mass ratio. 1 minus mass ratio. What is mass ratio? Mass ratio is mf divided by m0. What is mf? Mf is the final mass over m naught. What is final mass? Final mass is something when all the propellants have been used. Okay, have been used. Okay, is mf lah. So zeta is mp over m naught. Mr, mass ratio, is equal to mf over m naught. So this is definition. The thing is, if you want to memorize, go ahead. This thing is, I want you to have a better understanding rather than to memorize without knowing the terminology, the definition of each variables. Okay, right? So you have mass ratio, you have zeta, right? So this is the definition. So m, again, instantaneous velocity, instantaneous mass. So it can be either in this form, in this form, in this form, or in this form. Okay, all right. So all right. So this is the graphical representation. What is MP? What is MF? What is M naught, and etc. Okay. So the initial mass of the takeoff is, like I said just now before this, is equal to M naught. This is the sum of useful propellant. Useful propellant, which is MP lah, plus the empty vehicles, plus the empty of final vehicle mass. Okay. So M naught is equal to MP plus MF. Okay, m naught is equal to mp, which is the propellant mass, plus the vehicle mass. Vehicle mass ni including all the subsystem, the tank, the structure, the avionics, the payload, and etc. Okay, so like I said, mf equal to the sum of inert mass, engine propellant such as nozzle, tank, case, unused residual propellant, guidance, control, electronics, related equipment, and payload. So mf, you don't have propellant anymore. So m dot is mp plus mf. Right. So after the thrust determination, any residual propellant, I know that some of the propellant is not finished in the propulsion system, is considered to be part of the final engine mass. This include adequate propellant remaining in the tanks after operation, trapped in the pipe pocket, valve cavities, and pump awaiting the tank and the pipe wall. So now you have delta U. This is the change in the increment of velocity, change in velocity that you want. Because everything in the previous chapter, I have explained to you about Tchaikovsky equation. So this delta V, delta V velocity, now delta U, velocity, same velocity, is equal to minus C ln 1 minus zeta plus mu naught. So negative C, it is the velocity, the characteristic velocity. Zeta is mp over m naught, and u naught is the initial velocity. Okay, or you can bring the negative sign up, so you have C equal to C ln m naught over mf. What is m naught over mf? So m naught over mf mass m naught over mf is always greater than 1. Okay, m naught over mf, m naught is always larger than mf, so it must be greater than 1 lah. Okay, plus u naught. So you can, if you have zeta, you can use this equation. If you don't have zeta, you can use this equation. But the maximum velocity, when up is maximum, where the increment delta u that can be obtained in the gravity free vacuum with constant propellant flow and starting from the rest, means that the u naught, the initial velocity, is 0. So this is the equation. So u naught is 0, so you live by negative c ln 1 minus zeta lah. Okay, or okay, you can you can change this to negative c m naught over m naught minus mp. Again, what is mp? Mass of the propellant. Okay, what is mr? Mass ratio. What is mr? Mass ratio. So mass ratio by definition is equal to mf over m0. Mf over m0, it must be lesser than 1. Mf must be less, mf over m0 must be lesser than 1. So you can have like this, or if you want to remove the negative sign, so you're going to have 1 over mr, mass ratio. Okay, so this is the maximum speed, maximum increment, maximum increment lah. Okay, for the propellant. So looking at this diagram, the right one, so you have this engine mass. Engine mass only focuses on the rocket engine. And then you have engine propulsion system, including the tank, including the rocket engine. So this is empty mass, system mass. Propeller mass, okay, propeller mass is the fuel lah. Okay, it's the propellant itself. So full or loaded propulsion system mass is mp plus this one lah, empty propulsion mass. Bare vehicle is this one. Payload is the top one. So initial mass m0 is equal to mp plus mf vehicle. So the so the what do you call it, taking back the equation, the initial equation, okay, and then they try to, what do you call it, simulate in a graph or in a figure. So as you can see in figure 4.2, if zeta is higher, what do you mean by zeta higher? So like look at the graph here. Okay, let's look at the first one, first graph. Okay, zeta higher, what do you mean by zeta higher? Zeta higher, you, by the definition, zeta is mp over m naught. So zeta is equal to mp over m naught. If zeta is high, means that you are bringing more fuel. Okay, you are bringing more fuel, so the mass of the propellant is high. So if you look at the diagram, yes, if you bring more fuel, you can have you can have high maximum vehicle velocity. But of course, you cannot have 100% lah, because you need to carry the structure, the tank, and etc. So as zeta increases, the thrust increases, the exit, the maximum velocity increases, and the effective velocity also increases. Okay, and of course you have higher zeta, you can have higher specific impulse lah. Okay, that's number one. Number two, okay, if you have better specific impulse, okay, better specific impulse, for example, 200 seconds, 100 seconds for a second, you have good vehicle, maximum vehicle velocity, yeah, right? This mass ratio is m dot over mf. You can see that m dot, m dot over mf lah, mf, okay, m dot over mf. The higher the mass ratio, okay, the higher the mass ratio is good, but the maximum velocity comes into the constant value. Okay, All right. So from the above, which is this equation, it can be seen that balance mass fraction has a logarithmic effect on the vehicle velocity because you have a ln function there. Looking at this equation, by increasing the ratio zeta or mass ratio from 0.8 to 0.9, the UP, which is the unit velocity, UP, calling back here, the UP, where the U naught is equal to 0, okay, it can increase by 43%. That is how, that is the importance of this ratio. Mass fraction 0.8, okay, indicate that 20% of the total mass vehicle is needed for structure, skin, payload, propulsion hardware, radio, which is the transmitter, guidance system, lifting surfaces, and the remaining is the useful propellant. Again, useful propellant should be high in a rocket engine. When the mass fraction is 0.9, so then the MR is 0.1, or 1 over MR is equal to 0. So it is very, very important uh, to save the inert mass on each and every vehicle component, including the propulsion system. So in order for the the rockets to have a better performance, you need to have better zeta. And the final mass, so you have m dot m naught is equal to mf plus mp. So rearrange that, so mp is equal to m naught minus mf. So m naught minus mf, it is where it is burnt out, full burnt out. So this is the mass of the propellant. So the final mass, which is mf, include the payload, structural mass, empty propulsion system, plus a small additional mass for guidance, communication, and control devices. Any improvement in IS, which is the specific impulse, such as better propellants, we call better propellants parameter that we see in the propellants that they have higher heating value. Okay, heating value. What is a heating value? Heating value is the amount of energy it can give, okay, per 1 kilogram of fuel. Okay, so if you have fuel have higher heating value, for example kerosene A, okay, jet A, 42,000 42 megajoule, 42 megajoule of energy. So in 1 kilogram it can give energy 42 megajoule. Okay, so that is better performance indicators. Better, higher HV, maybe you have lower ignition temperature, colding point, smoke point, or all those, etc. All those are contribute to better propellants. More favorable nozzle area ratio. Yes, you want, what you want is, looking at the gas dynamics that you learn in nozzle theory. When you have a compressible flow, what you want is to have a better, what do you call it, exit, exit to throat area large. Okay, exit area AE over AT much larger. So this is what you want. Okay, the exit area in the divergent section, the exit area, you want it to be infinity as possible, as large as possible. But of course, there is a catch. You don't have, there's no such thing as a free lunch. If you want to have higher expansion ratio, area exit over area throat, expansion ratio higher, okay, the problem is that the angle will be so high. Okay, the angle will be high. You will see later in the nozzle design, okay, there is a law where you cannot extend the angle more than 30 degrees. Okay, more than this is a half angle. Okay, if you try to make angle big as possible, the thing is that the gas will separated from the surface of the nozzle. Okay, the surface inside nozzle. So when gas separate inside the nozzle, so you will lose some of the gas expansion. Okay, you will lose thrust, you lose energy. Okay, so we want that the propellant, the gas, fully attached to the surface. Okay, so that's why you cannot have large what do you call it, expansion ratio. Yeah, expansion ratio epsilon, we call this. Epsilon is equal to AE over A throat. Okay, you cannot use that. You want it to be, okay, favorable nozzle air ratio, you want it to be epsilon, but you have to tackle with the, what do you call it, separation. So that is why you see that in a rocket nozzle we don't use a conical shape like a triangular shape, okay, triangular shape, because the nozzle can be long. So that is why we use Laval nozzle, which is like a bell-like nozzle. The divergent part, the divergent part, after the throat, it will diverge area larger as possible, and then it is what do you call it? Close a little bit, converge a little bit, converge a little bit. So it's a bell, okay. So to avoid this separation, okay. Chamber pressure. This is what we want. Higher chamber pressure, better area nozzle area ratio epsilon, better propellant. This is what we want to achieve better ISP. So this reflects itself to improve vehicle performance. Higher pressure, of course, you have higher temperature. That's why you burn the fuel at high temperature. You can get high pressure. You have more energy to expel it out, provided that such an environment does not necessitate any excessive increase in rocket propulsion system in the mass, which will lead to a decrease in effective propellant fraction. So looking at the second equation, MP, which is the propellant mass, is equal to MF, which is the final mass, in bracket, E exponent to the power of delta U over C. Okay, this is where they got this equation lah. Okay, uh, all right, this equation. Okay, from that equation. So delta U is the thing that you the mission that you want to achieve. C is the characteristic velocity minus 1. So from this equation, actually it will determine how much MP, propellant mass, that you need to bring. When you know the propellant, how much the propellant mass to bring from the mission, okay, so you can estimate how much the avionic system or payload that you can bring together. Okay, so this is another important equation for you to know. So MP is equal to MF in bracket exponent delta U over C. So you, when you want to calculate this, make sure you calculate delta U over C first, and then you exponential, you minus 1 and then multiply by MF. Or it is M dots, which is the initial mass, in bracket 1 minus E to the power of negative delta U over C. Okay, it's still exponential function. All right, so that is the from the mission, and then you can calculate what will be what of the mass of the propellant that you can bring, or what how much the mass of the payload, the structure that you can tolerate. Okay, so next is forces acting on a vehicle. I won't finish everything today. I will split this into two, because we have 2 weeks to cover this flight performance according to the our schedule. So forces acting on a vehicle in the atmosphere, this one, going back to your aircraft or aerodynamics class, or maybe you have introduction to flight mechanics, flight performance, and etc. You all know this. L, which is the lift, is equal to CL half rho A U square. So CL is the coefficient of lift, half. Rho, what is rho? Density. A is the area. Area is the velocity of the vehicle. Okay, velocity of the vehicle. So similarly, you have D. D is CD half rho A U squared. The external forces. So when you have a rocket, what are the forces exerted into the rockets? Number one is thrust, which is from the nozzle. Okay, and then you have aerodynamic force. Okay, so when you have a rocket, so thrust force is from behind. Okay, you have thrust force and then drag opposite to the thrust, and then you have lift going up and then weight going down. Okay, gravitational attraction, wind or gust, and the last one is solar radiation. Those are some of the forces commonly acting on the body of a vehicle. So drag and lift force are given as a function of the vehicle's flight speed. So the higher the higher the vehicle, the much higher lift that you can generate, and also you have drag as well. Okay, drag due to the lift, drag due to the skin friction, and etc. Okay, the mass density and of the atmosphere it moves, and the characteristic surface area is okay. Now the question is A, the characteristic surface area. So the A in this equation, okay, I know that in our graph, the A we use is S lah, okay, the surface area of the wing itself. But here in rockets, A we assume it is perpendicular to the direction of the thrust. So when you look at the rocket, okay, when you look at the rocket, so in airplanes, you have the wing area. But for missile, which is you don't have wing, okay, space launch vehicle, it is the maximum cross-section area normal to the missile axis. What is a missile axis? Missile axis is the axis of this thrust lah. So A, which is the area normal to the missile axis. Okay, so you look the missile forward, okay, forward in front of you. So this lift and drag coefficient are primarily a function of vehicle configuration. So flight number and also angle of attack. You know angle of attack? Angle of attack is the angle between the chord and the flight trajectory. Yeah. Okay. That is angle of attack. So angle between the vehicle axis and the flight direction. So but wingless aircraft vehicles such as rockets, the effective alpha, which is the angle of attack, is usually smaller. So you are talking about not 0 to 1 degree. Gravitational attraction exerted upon any flying space vehicle by all planets, stars, and moon. We know that those heavenly bodies has mass. Any object which has mass, you'll tend to pull the vehicle. Okay, so looking at this figure 4.4, you can see that this is one is for the German V2 missile. So the several angle of attack based on the body cross-sectional area. So body perpendicular or normal to the missile axis. Okay, without exhaust plume effect. So it shows that, okay, let's look at the CD, the drag coefficient. Higher angle of attack, you will create higher drag, higher CD. Yeah? So this is the trend for the missile German V2. And actually for CL, okay, it reduces. Okay, it reduces. Higher angle of attack is good, but you also, although CL is good, CD also increases. So actually it's not that good lah. All right, so as you go faster, the CL reduces. Okay, you go faster, the CL reduces. Usually this one what do you call it, the 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 fin itself does not provide any lift actually. Okay, fin, you know, rocket, you have fin, right? Okay, fin usually does not contribute that much to this aerodynamic forces. It is meant for stability actually. It is meant for the stability, the location of the CP, the location of CG. CP is center of pressure, okay, and also CG is center of gravity. it plays a role on stability, and then also if it is guided rocket, so this fin can be helpful, okay, where they have what they call it a control surface at the fin, or this is much easier compared to have a gimbal thrust vector control at the nozzle. Okay. So this is the basic relation of motions of a rocket. So again, you have a rocket, and then this rocket you have lift pointing upward, and then you have weights pointing downward. You have drag to the left, F to the right. Okay, F, which is the direction of the flight trajectory. Yeah. Okay, and then you have, okay, when you have this inclination, so you have mg sine, mg cos. This is again dynamics cos. Recall back your engineering mechanics. Okay, F, everything is inclined, so you need to project. Okay, you need to project this into the axis, into the direction of L, F, D, and W, weight. Okay, go, since all the forces you have direction and magnitude. So using the Newton's law, Newton's second law, ma. So this is a, yeah? Du over dt is a, acceleration ma. So F equal to ma. So what are F? The summation of F. Okay. I know students kind of uh, misunderstood the beauty of F equal to ma. What is F? F is the force. What is M? Mass. What is A? Acceleration. But they did not know F must be the same direction as A. This is sometimes that the student miss out. F must be the same direction as A, acceleration. And this F is a net force. Okay, so this is ma, so the right part is F lah. So F is a net force. So the net force from what? F cos psi minus theta, which is this one. We assume that this is hello, hello. Can you hear me?
Yes.
Yes, yes. Okay, I send you some message. We
All right.
connection at the moment. Please wait. Okay, we are fine. Come back. Okay.
Vietnam heavy rain, huh?
Yeah, yeah.
All right. I hope the connection is okay after this. If not, please let me know. All right. So
Yeah, we are ready. Thank you.
okay. So the first equation uh, is very direct, and then the second one, it is the directional direction lah. So you have mu d theta over dt is equal to f sine, which is all in L direction, in y direction. So that is where you have sine phi minus theta, which is this direction. Okay, this direction, sine phi minus theta. And also you have lift going up, okay, and then mg cos theta going down. So these two equations is important, and then they have put m, which is mass, going down. So m going down. So that's why you have this. So when you have this, f over m cos phi minus theta, cd. Okay, this is where d and l, they took this equation. Okay, D and L, they took this equation, CL and CD, into the equation. So they have something like this. And then M with M can be cancelled out. So M can cancel out, that's why I got G lah. G and G. So M cancel out, so got G sin theta. M cancel out, G cos theta. So this is the function of M. All right. So looking at this equation, you have many factors to play around. Number one, the thrust. Mass, for this case, we assume that the mass doesn't change. The vehicle mass doesn't change. But logically, the mass change. Why? Because the fuel is burned. Okay? But now we maintain that the mass doesn't change. And also depends on the direction. The phi, which is the direction of the, what do you call it? The angle between the horizontal and the direction of thrust. Theta, and then you have velocity u, and then you have area doesn't change. So you have many consideration to take consideration. So because of this, there is no general solution that can be given to this equation, since TP, which is, what is TP? The time to burn out, U, the vehicle velocity, CD is the coefficient of drag, CL, the coefficient of lift, density, theta, and or phi may vary independently with time, mission profile, or attitude. So in more sophisticated analysis, other factors can also be considered, such as any propellant used for propulsive purposes, attitude control, or flight performance, because rocket propulsion systems are usually tailored to fit the specific flight mission. Different flight performance parameters are maximized or optimized for different rocket flight mission or flight regimes, such as delta U. Okay, which is, this is the mission. Delta U is important. Range, orbit height, and shape, time to target, or altitude. There are always a number of trade-off in selecting this best trajectory. Okay, if you look into the trade-off, okay, let me finish the sentence. So for a fixed thrust, for example, for a fixed thrust, the trade-off is between the burn time, drag, payload, maximum velocity, and maximum altitude or range. Okay, let me put an example. Let's take an hobby of rocket, sounding rocket, hobby rocket. Okay, so hobby rocket, they launch, okay, for example, to achieve a certain altitude. Okay, so they launch until the MECO, and then you calculate the projectile. Okay, so there are, using this relation, the Vx component and then the Vy component. I hope you can recall this in physics. I will also share you the equation for this parabolic curve. Okay, so you can see that you can play around with the angle. Okay, you can play around angle. Let's say, okay, let's say the 0 angle is the horizontal, and then 90 angle is the vertical one, so 0 to 90. So for example, that if you want to take a better height, when you mean altitude lah, okay, better height, so you can go near to 90 degrees, 90-degree angle. Okay, so 90-degree angle. But if you go to, for example, 75-degree angle, having a MECO value, for example, velocity is certain, what do you call it, certain value, weight, certain value, your rocket doesn't go far. Okay, it doesn't go far. If you have higher angle, 75 degree, for example, so it doesn't go far, it go high. But as you reduce the angle, you can the area that it cover increases until 45-degree angle. Until 45-degree angle. With the same rocket and MECO, you only play around with the angle. You only play around with the angle. So if you reduce the 75 degree to 60 degree to 45 degree, 45 degree is a degree where you can shoot the rocket furthest, but not highest, furthest. If you go much below than 45 degree, for example, 25 degree, 15 degree, it does not travel that far. This one is according to free, what do you call it, assumption, gravity free, drag free, and as well lah. Okay, that is the what do you call it, the effect if you are playing with the angle. Okay, so that is why you want to your mission to go furthest. So these are the angle. If you want to go for high, why you need to go for high? Maybe you want to avoid radar, something like that. Okay, so they shoot higher at higher angle lah. Okay, so that's a trade off, and then of course, if you want to increase your burn time, okay, another trade-off condition that I can share you based on my experience. If you want to increase the burn time, so you are delaying the MECO, burn time, TP, burning time. You want to increase the burning time, the MECO, main engine cut off. Okay, increase the burning time. Okay, fine. You need to bring a lot of propellant, which then limit the payload. So this is a trade-off lah. Okay, and then another thing, if you want to bring a lot of propellant, which is zeta, you want to increase the zeta, your body of the rocket will be fatter, will be big, and this will increase the surface area, which resulted in increase in drag. So these are the trade-off. Okay, all right. So nothing is free lunch. All right. So next is to continue. Okay, now let's go for the two-dimensional category trajectory, x and y. In a single plane, no wind forces, and a stationary Earth doesn't rotate. Acceleration in the direction of flight given below, where TP is the burn time and the zeta is the propellant mass fraction. Okay, so du, coming back at the equation du here. Okay, so you have C zeta. Again, I don't expect you to memorize this. My students, I don't want them to memorize. That's why I'm giving all the assessment open book. But they must know and understand the variables that is used. Okay, what is C, what is zeta, and how to use it, because this is the general formula. If you are looking at 90 degree, so sine 90 is 1. So sine doesn't appear anymore. So this is why you need to know what to use it, or which equation need to use, and how to use it, and when to use it. All right. So after substituting everything, so this is the function du, which is acceleration. Du over dt is acceleration. Okay, acceleration. So acceleration, c zeta over tp, blah, 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 is a very long one. So for the vertical trajectory, so this is what I'm saying. When it is vertical, sine 90 degrees, so you have g, only the gravity. So cd half rho u square a, etc. Okay, now to make your life much easier, B, by definition, they take all the here. Okay, they assume half rho u square over 1 zeta t dp as b. Okay, so this term is b. So thus, okay, so thus it becomes something like this. The bottom one, the bottom right one. So what is UP? UP is the maximum velocity. Recall back. Okay. So this is usually what. So UP is the maximum velocity when U naught is equal to zero. Okay, maximum velocity that the rocket can achieve. All right, coming back. So it is C. Okay. How is it got UP here? Integrate lah. Okay, integrate. Okay, UP, you have du, so you integrate this one with respect to t, so you have this equation. So negative c ln 1 minus zeta gt etc plus u. Okay, when aerodynamics forces within the atmosphere may be neglected, so you have this one. Okay, this one, this is the full general term. This is the full general term. Negative C, blah, 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 B, C, D, A. This is full general term. But, brothers and sisters, if you have no atmospheric drag, so when the atmospheric forces within the atmosphere may be neglected, for example, in vacuum operation, and when no booster or means for attaining initial velocity E naught is equal to zero are present, so the velocity at the end of burning reach the vertical ascending trajectory become simply, so from this, U naught is zero. You don't have aerodynamic forces, which is this one, this term is equal to zero because CD is zero lah. So you have something that negative C ln 1 minus zeta GTP. Okay, so this term is zero. The first, second, the third term is zero. The fourth term is zero. So becoming something like this. This is the maximum one lah. Why you need to calculate the UP? Because this is the maximum velocity at a cut-off point. At MECO, when the thrust, when the fuel finish burn, so this is the maximum velocity UP. So when this velocity you can determine, so you will know how far it can reach the apogee and how far it can travel in the horizontal distance. So that is why they want to calculate this UP, the cut-off velocity. All right. So in a simplified case, A0, which is the acceleration, is Fg force, the thrust, multiplied by the G over the weight minus G initial, where AO and GO is the initial takeoff acceleration. If this one is given lah. In multiples of the in multiples of the sea level gravitational acceleration G naught and F thrust to weight ratio at takeoff. If in simplified case, if thrust to weight ratio is given, so you can simply calculate the acceleration. Okay, simply calculate acceleration. So that is why for large surface launch vehicle, for example, SpaceX, Ariane, what do you call it? Another one, Roscosmos, or all those launch vehicle rockets. The initial thrust to initial weight ratio, thrust to weight ratio, usually small, between 1.2 until 2.2. What do you mean by 1.2 or 2.2? Let's take 1.2. It means that the thrust only 20% more than the weight. But 2.2, 2.2 times than the weight. So actually you can see that during the takeoff, during the launching, the thrust to weight ratio is small, means the acceleration is small. So that's why in launch vehicle, you can see that the rocket move quite slowly during the initial phase. And then it start to increase the acceleration lah. Okay, but small missile, for example, air to surface, or surface to air types is usually larger. Usually larger means initial acceleration takeoff is higher. So you are talking about 50 to 100 times higher than the weight itself. So for rocket launch, for missiles, for example, it accelerates faster initially. All right, so so this is the what do you call it? Some of the mathematical formulation. I won't. I will save this space flight later on because this one involve. Eh, yeah, let me check. What is slide number? Okay, space flight is 14. So we are already in the middle. So I have to stop here. Slide number 14. We will do this next week. So, um, like I said, in this chapter, uh, as compared to the previous chapter, what you must do is you must first identify what is the mission that you want to go. Okay, so the delta U that you want, UP that you want to achieve, uh, and then from that, after the Mako, then you can determine what is the apogee and then the distance that it cover. From that, you can also calculate the mass, the propellant mass that you can bring, and then you can design the nozzle using the previous equation lah. Okay, in the previous chapter. All right, so I do have several equations, fundamental equation for a rocket's flight path. I can share you, I can include this in the slide later. This is where you achieve the MECO. You want to predict how far that the rocket will reach, how high that the rocket can go in the apogee. Okay, so it is the y function, which is yx, and then the height maximum, y maximum, and then the instantaneous x and y direction after the MECO, and also the x distance, which is the surface distance. This is a fundamental equation for rocket flight path. If I have, it's much easier if I can write lah. Never mind. I will put this in the slide, update the slides, and share this with you. This because this is important to determine the the rocket altitude, apogee, maximum altitude, and the farthest distance from to the impact. Okay, all right. Of course, we assume all those four assumptions. Nah, no gravity. Acceleration of gravity is assumed constant. Bukan, it is not no gravity. Gravity we assume constant. Okay. Area neglect air resistant, assume earth flat, and also we assume that the earth rotation no impact. Okay, I owe you the equation, the fundamental equation for the rocket flight path. I don't want to discuss on how they derive this, but I straight away share you the equation. Okay, so I will update the slides. This is the equation. What you have seen in the slide. This is a equation where the mass of the propellant, where the mass of the vehicle is known. The one that I want to share later has nothing to do with all those mass, only related to the projectile motion. Okay, you must differentiate this equation that we studied here. Okay, mr, zeta, and c, and etc. Those CD and etc. Those are relation where you consider the mass, but the equation, the flight path equation, there's nothing mass given. Mass is not being considered. Okay, we only can calculate the, what do you call it, the direction, the distance, the measurement of the distance, and etc. Okay, because this one, this equation, we use Newton's law, and this equation, the one that I will give you later, it is only on the y-x direction. Okay, the trajectory only. Okay, it means what? It means that you can use both. One is without mass, the other one is with mass. Okay, so we will continue. I have to, Is I finished early. I finished early. So, any questions from the students that you would like to ask?
Yeah. Thank you. So no worries. We can continue next time because I also have some discussion with the student
Oh,
regarding the quiz.
oh,
So
okay.
okay,
So,
so
so the quiz.
we don't make a take a break so we can finish earlier. But
Oh,
already very student were introduced with fundamental equation and
mm,
um, detailed explanation, so they can work further on that.
okay. So
Uh,
I owe you two things. And one is the equation of the flight motion, and then another one is the calculator.
okay.
The Excel file that my students wrote in the spreadsheet.
Yeah,
I will share this in the WhatsApp, and I hope that Dr. Hugh, you can share this with the student.
yeah, sure. Thank you.
Okay.
Thank
So,
you. See you next week.
okay. See you, Desi. Thank you so much. Bye. Bye, everyone.
Bye. Have a nice afternoon, evening. Thank
Stay
you.
safe.
Yeah.